Hi, Amy. How are you doing?
Oh,
Good.
sorry. Hi, sir. I'm good. Thank you. How are you?
Good, good. Nice to see you. Long time.
Yes, long time.
Yes. How are your
Nice.
tests going on?
Yeah, good. There's a lot of had a lot of chemistry and biology tests lately. That's why I had to put like maths on hold because when I did my maths test, yeah, I did the senior maths challenge. It was definitely challenging. Uh,
Okay.
I definitely attempted like the 1 to 15, a couple of them, and then one of the ones on the harder ones further down. But like you said, you can either just lose 1 mark. It was kind of a 50-50 after process of elimination, and then you can either lose 1 mark or gain 4 marks. So I was
Okay.
like, just take it.
That's good.
So yeah, I tried.
Yeah, nothing to lose. It was, I think, a good experience for you, and surely it is going to benefit you next year, right?
Definitely, yeah.
Perfect. So I heard you're doing extremely well in chemistry also.
Yeah, I had some like tests that we had to come in, and we didn't prepare for it. It was just one of these tests that he would just give, and you have to just know the stuff. And yeah, I got full marks, so
That's great.
quite
That's
happy.
extremely
Yeah,
happy to know that, right?
thank
So
you.
all around, you're doing so well. I'm extremely happy for that. So now you have started with mechanics, right?
Right, yeah.
So I thought we'll take up the basics. We'll look into the position time graph today, and we'll see how to read information from position time graph. And then
Okay.
in later videos, we'll discuss more about kinematics when we'll find velocity, acceleration, all those stuff, right?
Right.
So let's begin with that. Here is the video material which I have prepared for you. Okay, so you can see my screen now.
Yes, I can.
Perfect. So we'll talk about the position time graph as shown here. So as you know, these things which I've written here, position, displacement, velocity, and acceleration, all
Hmm.
these are vector quantities. That means they have magnitude as well as direction. Most of the time, you had been earlier working with distance and speed. Those were scalar quantities which had only magnitude but not a defined direction, correct?
Hmm.
So that is one difference between the two. Now, to take a few examples, you can see some variety here. We'll begin with a very simple graph, which is all a position time graph. So on the graph directly, you can read the position from the graph. Displacement is change in position. So we sometimes also call this as displacement time graph, since you can actually read the displacement also directly from the graph, correct? Okay, I've also written velocity time graph here to give you an idea. Velocity is rate of change of displacement. So the slope at any particular point or during the interval will give us the velocity, correct? For a straight line, of course, the slope is going to be constant and therefore the velocity will be constant. This red line shows the velocity. However, the units are not perfectly matched since for displacement, you will notice that the units I have used are meters. Perfect.
Hmm.
But when we talk about velocity, the units will be meters per second, correct? So units are different. So do not take this 5 as 5 meters per second, but yeah, it is 5 meters per second. Do not take it as 5 meters, right? Because
Right.
after a velocity, right? So I didn't complicate the graph by writing both the units, but velocity means rate of change, and therefore it should be meters per second, correct?
Hmm.
So one by one, we are going to discuss all these graphs. In all the graphs, one thing is common, and that is the acceleration is constant. So we'll see what is going to be the acceleration. Acceleration is rate of change of velocity. If velocity is constant, like shown in this graph, then acceleration will be zero, correct? But if velocity will be a straight line, then acceleration will be constant, but will have a value other than zero.
Oh, okay.
So in any case, the acceleration is going to be constant. It could be zero or non-zero. It could be positive, it could be negative. So those are the type of examples which will show you how. To
Hmm.
find velocity, every place we have taken gradient. So if there is a curved graph, for example, shown right here, so this one is a curved graph for displacement. If I want to find velocity at any point, I will have to draw a tangent at that particular point. Slope of the tangent at that particular point will actually give me the velocity at that point. And this velocity is called instantaneous velocity. So when you have a curved surface, curved graph as shown here, in that case, you may have to find instantaneous velocity at a couple of points and then join them to get the velocity graph, right?
Yeah.
So we have assumed this to be a parabolic path, and the rate of change for a parabolic path will follow a pattern which is of a straight line. So velocity graph will be a straight line shown here. So we'll see how to draw all this in details now. But this concept is clear to you?
Yeah.
Okay, let's go through some definitions. Kinematics and dynamics, these are two confusing terms. Now, what is the difference between kinematics and dynamics? Can you tell me, please?
Don't know what they mean. So no, I don't
Oh,
know. Like I haven't heard these terms before.
I see. So, can you please read what is kinematics?
Kinematics is the branch of physics that deals with the description of the motion of objects without reference to the force or agent causing the motion.
Perfect. And can you read dynamics?
Dynamics is the branch of physics that deals with both the motion of bodies and the forces that produces it.
Perfect. So, in dynamics, we also study the cause of the motion, right? The Newton's law come into picture. The force actually changes the direction of the motion, correct?
Mm.
So that is where the dynamics comes into picture. So in the first unit, you have not seen force. You have only seen velocity, acceleration, displacement, position, correct?
Right.
So that is all about kinematics. We are not really interested in what is causing that. You understand? We are not interested in what is causing that change. Perfect.
Mhm.
So that is what kinematics is. But when we take into consideration the force which may change the motion of a particle, then it is dynamics, correct? The other definition, vectors and scalars, you know fairly well. So what is the difference between vectors and scalars?
Vectors have like a direction. It's a quantity with a direction, where a scalar is just like that magnitude or like that quantity.
Perfect. So here are the examples of vectors: position, displacement, velocity, acceleration. So these are all vector quantities where position is actually the in the coordinate plane will normally reflect the position of an object with the coordinate points. So position is a place where the object is located. It has a point of reference and direction. So normally in our graph, that point of reference is going to be the origin. Is it okay?
Yeah.
Displacement is a vector quantity. So we'll see displacement could be positive or could be negative, but it is basically change in position in short, correct? Velocity is rate of change of position, and acceleration is rate of change of velocity. The other quantities are distance, and also sometimes we say directed distance. Well, let's be very clear about it. Distance is a scalar quantity. Whether we write directed or not, it is a scalar quantity. Even directed distance is a scalar quantity, right? It has
Oh,
only the magnitude. Perfect. Or when we say directed distance means we know that this is the direction of the distance, but we are only interested in the magnitude. So let us not confuse
oh,
with
okay.
displacement at any instance of time. Okay.
Yeah.
With that, let's begin with our examples. So the very first example here is of uniform rectilinear motion with constant velocity. So when we say uniform rectilinear motion, it means we are talking about a straight line motion, correct? So
Oh,
most of the cases, when we discuss this uniform rectilinear motion, we assume that the particle is moving along the x-axis. Is that clear to you? So
okay.
particle is moving along the x-axis, correct? So that is what we are assuming. And the time is the major factor. Time is always changing. We
Hmm.
are always checking the position of the particle moving along the x-axis from a reference point. And this reference point for us is going to be the origin.
Okay. Yeah.
So when the particle is moving away from the origin towards the right-hand side, we say that this is a positive motion. And when it goes towards the left, then we say it is a negative direction. Is that clear to you?
So is the fixed point always the origin, or is it just in
Origin.
this question? Oh, okay.
Origin, yeah. Sometimes we may change it, and when we change the point of reference,
Hmm.
then instead of writing, for example, x0, we may write x minus x0. I mean, because that
Because it moved.
translation will be
Yeah.
different. Then we will say, well, the initial point was that, and now it is from this point. So we may use sometimes transformations, but not in this particular video. We are not getting into that complication today.
Okay. Yeah.
Okay, we'll keep it simple, but we'll understand all the concepts. So now, position of an object is shown with reference to the fixed point, and that is going to be the origin. Now, what you have to do from the given graph, which is the green line shown to you, so we're basically trying to describe this particular graph, which is the position time graph, right? So we are always describing a position time graph. So, so you need to describe displacement, which is change in position, and find velocity for the given graph. That is the exercise which we are going to do. So what I've done here is basically split it into small units. So we're saying in the first second, what is happening, in the second seconds, what is happening, right? And then we will elaborate on this. In the very first second, you can see that the object starts from a position which is minus 10, correct? So it is like 10 units to the left of origin. You can see
Hmm.
minus 10. And then after 1 second, it reaches this particular point, correct? So it is now closer, but it's still 5 units away from the origin on the left hand side. But see, it has covered a distance of 5 units. Now, this distance is covered in the right hand, going towards the right, right?
Hmm.
You can say east, and it is considered to be positive. So the displacement is positive 5. Displacement in general, we will write with delta D, which is change in position, right? That is the definition of displacement, change in position. So like P2 minus P1, you can say, right? Which will be
Yeah.
so in this particular case, minus 5 minus 10 will give you the answer, which is 5 meters. Is that clear to you? So that's
Hmm.
how we'll find displacement within the first second. Now here is the other term, which is in the second. You understand now? When we say in the second, we are interested in time from t equals to 1 to t equals to 2. That is the second. Okay?
Okay.
Sometimes this term is very confusing. So it is from t equals to 1 to t equals to 2. Is it okay? So
So
that
the
is
first second is 0 to 1.
first second is from 0 to 1. Yeah?
Okay.
Very important to understand, because in word problems they use these terms and it becomes very confusing for students to understand.
Mm.
So at both the times, we will directly read the position, which is minus 5 and 0. Taking their difference, we get displacement again as 5 meters. Perfect. So that is how you can find displacement along this path for any interval of time. Correct?
Yeah.
You can directly read the position. What is the position at t equals to 4? You can read from here 10 meters. Correct?
10. Hmm.
Likewise, you can also read the position from the graph. So you can read position, you can find displacement, you can, so we'll have one more example. Can you do this? Displacement between t equals to 1 and t equals to 4. How will you do this?
So at t equals to 4, the distance is 10 meters.
Perfect.
And then at t equals to 1, um, what is it? Minus
Minus
5.
5, minus
Yeah.
5. Two
So
small
when
units.
you do 10 minus 5, so 15 meters.
15 meters. Perfect. Now let's try to find how do we find the average velocity. So when I say average velocity, that means during that interval, it could be plus or minus at different instance,
Mhm.
but overall, what is the average velocity? So we take the whole displacement. In this particular case, we'll find the average velocity at t equals to 1 to 4 between this interval. So
Mhm.
we'll read the displacement and then divide by change in time. So it is basically change in change in position divided by change in time, which gives you the average velocity. So d4 minus d1 divided by 4 minus 1 gives you 4 meters per second as the average velocity. So average
Mhm.
velocity is between an interval of time. Is that clear to you?
Interval of time. Okay.
Another term is instantaneous velocity. So that is the velocity in general. So when I say velocity, it will mean instantaneous velocity, not average velocity. Okay.
All right.
So velocity is rate of change of displacement, right? It is the slope at any point on this graph. It is at that particular point, what is the velocity? So
Okay.
for a straight line, it will be same as the average velocity because, the slope is same, correct, at each point. So in this particular case, the instantaneous velocity is also 5 meters per second. Is that clear to you?
Yeah.
So, as mentioned here, you can see that. Can you please read this part?
Uniform linear motion is one-dimensional motion along a straight line with a constant velocity. Motion in one direction is considered positive and the other is negative. Normally, movement along east or north is considered positive direction.
Correct. Now, sometimes in the word problems, they may say the car is moving towards west. Well, you can say that for you, the west is positive direction. You could do that, right? If
Yeah.
everything involves that, why to write always negative, negative?
Yeah.
So it is a convention which you need to define. By default, we say east and north is positive. Clear?
So
Yes.
north, east, south, west, you're saying these two are positive. Or can
Correct.
any of them be? And then that means west and south are negative.
If I say a car is moving north, we will take that as positive direction.
And northeast?
No, then it will have to be split. We'll see that.
Oh, okay.
Yeah, we'll have to split into components and then work on it, correct?
Okay.
Well, if everything is along the northeast, we can define that this is our positive direction, that we can work along that direction. Not a,
Right. Okay.
yeah. Okay, example number two. Uniform rectilinear motion in one direction is almost the same thing. However, there is one particular difference. You can see from the graph that in the first part, the object is moving, and then as the object moves, the position is changing and it is increasing all the time linearly. Then at one instance, which is t equals to 4, the object comes to a standstill. So at this particular point, object is stationary, correct? So sometimes you
Mhm.
may have to describe the position time graph. You can say the object is stationary for some seconds, which can be read from this graph, and then again it moves forward. Overall, the object is not turning, but it is only moving in the same direction. Now,
Mm.
this kind of a graph also will give you one important thing is during calculations you'll find that if you're not changing the direction, in that case the magnitude of displacement and distance will be same. So distance traveled will be same as the magnitude of displacement if it is not turning, correct? That is
Okay.
important to see. Second, the slope is different in these three intervals. First, it is increasing, correct? So the slope is constant. Then it is stationary, slope is zero, velocity is zero. And then again, it is increasing, but at a slower rate. So slope, which represents the velocity, will be slightly lesser than what it was in the first part of the graph, correct?
Mhm.
So normally questions involving this will tell you to write a story based on the diagram given to you. So an object starts at a position, goes with some velocity, and the velocity can be calculated from the slope itself, rise over run, correct?
Right.
That is how we will find the slope and then we'll describe it as a story. That could be a type of question, correct? So this is an exercise just to see how to analyze that kind of situation. So
Mhm.
again, we have three different intervals, one from 0 to 4, then from 4 to 8, and then from 8 to 12 seconds. In the first interval of 0 to 4, we see that the displacement is is increasing. It has increased to 8 meters in an interval of 4 seconds. Therefore, the velocity is 2 meters per second. In the second leg, 4 to 8 seconds, displacement is constant. It is zero. It is not changing. And therefore,
Right.
velocity will be zero, right? It is object is stationary at this particular point. And in the third interval, the object further moves away. So the distance uh, increases, displacement also increases since the position changes. Change
Mm.
in position is 12 minus 8, which is 4 meters, and change in time is 12 minus 8, which is also 4. So we get velocity of 1 meters per second. So velocity is kind of half in this particular region as compared to the first one, correct? Now, can you tell me what is the total distance covered in 12 seconds?
So total distance.
Yeah, covered in 12 seconds.
Um, do you just add the displacement? So from 0 to 4 seconds, you said the displacement was 8.
Yes,
Then 4 to 8, you said the displacement was 0. And then from 8 to 12, you said it was 4. So 8 at 4, 12.
right. Fortunately, your answer is right because the displacement was positive. So basically, when you're trying to add the displacement, you have to add the absolute value of displacement. Okay.
Oh, okay.
That is very important. Now, in this case, since it is going, you can see initially it was at zero, then it reached a position which was 12 units away, and therefore we know that the distance covered in this particular case is 12 meters, correct?
Wait, sorry, how did you get that again?
So from the graph itself, net change in position is this, right? From 0 to 12.
Oh, right. Yeah, yeah.
So that is the net distance you could straight away read since there is no
Yeah.
turning point.
Oh,
Since there is no turning point, the
yeah.
final position is giving you the total distance, okay?
Mhm.
Total time is 12 seconds. In this case, you can also find the average velocity. The average velocity will be total time over, total distance over total time,
Mm.
which is 12 over 12 equals to 1 meters per second. Do you see that? So we could also calculate average velocity for the whole duration from 0 to 12 seconds. Is that clear to you?
Yeah.
Perfect. Can you please read the last part?
Acceleration in each interval is 0 as the velocity is constant. Velocity and acceleration is not defined at the points showing discontinuity or corners.
So at these particular points, specifically, because they are rate of change. So if you look at the rate of change, then rate of change approaching from this side is not the same as from the other side, before and after. Since
Mm.
they are different, at these corners, velocity and even acceleration are not defined, right? But immediately before this or immediately after this, they are all defined. Is that clear to you? So at
Okay.
corners, they are not defined, right? Okay,
So
yes.
wait, is it both acceleration
And
and
velocity, yeah,
both
velocity also.
acceleration? Okay.
Because velocity is also rate of change of displacement. So
Right.
it seems to be 2 when you are approaching and 0 after that. So we don't know at corner which one to take. So there is an
Right.
ambiguity, right?
Mhm.
Perfect.
So both acceleration and velocity are undefined at corners and discontinuities.
Yes.
Okay. Yeah.
In example 3, I made a variation. I've changed the direction. Do you see the third leg? First two are
Yeah.
exactly similar to what we had just discussed. And now we'll focus on the third leg, which is the position is actually decreasing. That means the displacement is negative in this interval, correct?
Mhm.
So as earlier, from 0 to 4, the things were pretty same. Displacement of 8, velocity of 2 meters per second, 4 to 8, 0, 0. And now duration 8 to 12 seconds. As you can clearly see, what is happening here is that d12 minus d8, right? Final minus
Mhm.
initial position is 4 minus 8, which is negative 4. So since you can see the position is decreased as with reference to the origin, the
Mm.
displacement is negative. Object is now actually traveling towards the origin. It's not going away. It's towards west. It is going now, correct?
Right.
Therefore, this is change in position. So the displacement is -4. The velocity, which is displacement over the time, will also be negative in this interval. So -4 divided by 4, -1 meters per second, correct?
So that's the velocity for that section.
This section only. The other two are same as before. Perfect?
So you have to put the -1
Of
because it's
course.
going in the negative direction. Okay.
Yes. That is
Can
right.
you write,
Yes.
oh, sorry, can you write 1 meter per second in the negative direction, or do you have to, like with words, or do you have to put the minus? Do you think
Minus
it's
is
better to put
better.
the minus?
Minus.
Okay.
Sometimes when they say east, west, and north, south, well, you could
Yeah.
say south or west. You could say that, right?
Oh,
But
okay.
in a question like this, it's better to write -1. Now, distance and speed are scalar quantities, as we know. Now, can you tell me how will you find the distance?
Um, so with the distance you said was from 0 to 4 was 8. That's 0, and then that distance there is 4.
Correct.
So 12.
+4.
Yeah.
So total will be +12. So whether you went forward or backward, you covered that
It
distance,
doesn't.
right? So it
Yeah.
is a
Right.
scalar quantity, and therefore it has to be added, right? So it is 12 meters, and average velocity in this average speed, I should say, average speed is still 1 meters per second. Do you see that? Speed is the distance divided by time. So the total distance is 12 meters and total time is 12. So average speed is 1 meters per second. Do you see that part?
Wait, why can't you say average velocity?
Okay, now calculate the average velocity. What is the average velocity in this particular case?
So it's the change in position
Correct.
over change of time. So the change in
So
position is
4 minus 0 over 12. Because starting was 0 and this
Mhm.
position final point is at 4 units. So 4
Yeah,
minus 0 over total time taken is 12 units. So it is 1/3
meters per second.
and is not the same as the average speed. Do you see that part?
Oh, yeah.
So
So it's
average
about
velocity is different from average speed,
right.
especially when you have a turning point. So if you have a turning point, then all scalar quantities are different. Their magnitudes are all different.
Oh, okay.
Perfect. Very important. So can you please read this part?
Um, what the red part?
Yes.
Isn't that the same as? Oh, I'll just say it again. Acceleration in each interval is 0, as the velocity is constant. Velocity and acceleration is not
Okay.
defined at the.
It's the same thing. I thought I wrote about average speed. So it is to be noted in this particular example that the average speed may not be same as average velocity, correct? Especially
Yeah.
when there is a turning point. Example 4, distance, net displacement, and average velocity. Now we are going to focus on average velocity. You have a clue about it, correct? So I
Yeah.
think we're in a good position to answer this particular question. So here we have a position of an object is shown with reference to fixed point and the origin. It is, I think, the similar graph to what we had drawn earlier. Now we'll focus on the total interval. So this time, the total interval from 0 to 12, what is the time duration? Time duration is 12 minus 0, which is 12.
Mhm.
And displacement, net displacement is 4 minus 0, which is 4. And therefore, the average velocity as we calculated last time is 4 over 12, which is 1/3. So 1 over 3 meters per second. Perfect?
Right. Yeah.
On the other hand, clearly, we have given you again the calculations for average speed, time interval being 12 seconds, right? And the distance traveled is 12 meters. Average speed is distance over time, duration. So it is 1 meters per second, correct? So consider final and initial displacements for velocity. So for velocity, we are only considering this net. Do you understand?
Yeah.
That is how we do it, correct? Now, can you please read this part?
Average speed is not the magnitude of average velocity. if the object changes direction, then the average speed is greater than the magnitude of average velocity.
Very important. So this
Oh,
could be in a test, right? Very simple statement. Many times students get confused over this.
could I just take a picture of
Sure,
that?
sure, sure.
So that's gonna be like a nice like double check. So if you like got a value that was, if your speed was less than your average velocity, then you know you've gone wrong somewhere.
Gone wrong.
So,
Yes, for sure.
right. Yeah.
For
It's
sure.
good to have those like key little things just to double check, you know.
Correct. So till now, we were talking about the displacement graph where we saw straight lines, correct? Combination of
Mhm.
straight lines. But now we have one where the graph is curved, right? It's kind of parabolic. You see this green curve, right?
Yeah.
So that curve directly indicates that now the slope at every point is not the same. It is not a straight line. It is going to be different. And clearly, at the origin, it is zero, and it increases as we go because the tangent drawn at every point on this will give you the slope, and the tangents are with increasing slope. The gradient is increasing as we move towards the right.
Yeah.
Correct? For a parabolic path, we will also note that the rate of change is kind of a linear function as shown in the red graph here, which actually represents the velocity, which is the rate of change of position or displacement, correct?
Okay.
But we'll do all our calculations and we'll try to understand one particular point. How do we calculate instantaneous rate of change from the graph? That is
Mm.
the whole idea. So here we have a non-uniform linear motion. Motion, a position time graph is not a straight line for non-uniform linear motion. We have assumed that this graph follows a function which is d equals to 0.1x squared. So using this, I have graphed this green curve which shows the position. Okay, you have to do these two parts: find displacement and average velocity on the interval 0 to 5, and second is determine instantaneous velocity at t equals to 5. Correct? So these are the two things which we do. So part A is kind of straightforward, which is find displacement and average velocity in this interval 0 to 5. So the interval is from 0 to 5. That is the point which is marked for us. Displacement is change in position. Position is 2.5, as you can read from the graph, starting from 0. So the displacement is 2.5 minus 0, which is 2.5. Correct? That's the displacement.
Yeah.
Velocity, the average velocity, is displacement over change in time, which is 5 is the change in time. Dividing, we get 0.5 meters per second. So that part, average velocity, is 0.5 meters per second. Now, we'll focus on the instantaneous velocity at this particular point when t is equals to 5. So for that, you have to draw a tangent line. So this dotted line shown here is the tangent at point A, which is t equals to 5, and
Yeah.
displacement is 2.5, position is 2.5. So when you draw this line, in that case, I've just taken point, so you can just drop you can find rise over run, correct? To make a triangle,
Yeah.
and measure the rise over run. So from the coordinate points, I've written here, it is 5 minus 0 over uh, 7.5 minus 2.5. Those are the coordinate points. And so I get instantaneous velocity at 5 as 1 meters per second. Do you see that? So that is how you find the instantaneous velocity. So on the graph, at 5, I mark this point as 1. Is that okay? Of course, the units are meters per second, not meters. So I made
Right.
the point as 0. Now, the idea here is, I'm just extending this. If you have to draw the velocity time graph, in that case,
Mhm.
you know that at origin, it was 0, right? It is tangential, just started. And therefore, you can connect these 2 points and extend to get your velocity time graph because it is assumed to be a straight line.
Oh, okay. So but if they didn't tell us find the instantaneous velocity, but then they just went straight on to sketch the velocity time graph, would you just draw a tangent at one of the points and then you find the gradient, join it to the origin, and that's your line?
Very good. At least use
Oh,
2 points. At least use 2 points.
at least 2 points. Okay.
Right. So you are very sure, well, the second one is here and you are through it, correct?
All right.
One
Okay.
point can work for you, but use 2 points. Graphical results are not very accurate because, when you draw this tangent, your line could be slightly tilted and that will give you a huge error, correct?
Right.
So use 2 points and then average it out. That'll be the best thing, okay?
Okay.
So that is how you should draw the graph, which I've drawn in red color in this particular diagram. Is that clear to you?
Yeah.
Now you see, acceleration is rate of change of velocity. So slope of this particular line, which I've drawn in red, will be the acceleration, right? So I can take up 2 points and find change in velocity over change in time and then get the value. We already worked out that at 5, the velocity is 1 meters per second. So 1 minus 0 divided by 5 gives me 0.2 meters per second square as the acceleration.
Oh, okay. So the gradient of the line on the velocity time graph is your
Yes,
acceleration.
correct.
Okay.
So here is the definition of instantaneous velocity. It is defined as the small increment in displacement divided by small increment in time. That gives you the value, which we also write as where the limit delta t approaches zero. It is to signify that, that triangle which you're trying to make
Mm.
that has to be having very small change in time. Then your accurate result. Perfect.
Yeah.
So that is how we will be actually finding on a curved surface both acceleration and velocity.
Oh, okay. Yeah.
Example 6. So in this case, what I've done here is I've changed the first part, made it the same parabolic path as we understood in example 5, the previous example, kept the other two quite similar to our first three examples, correct? Now, can you please read this question?
Yeah. Um, the parabolic path in the first 4 seconds indicate that the object starts with initial velocity of 0 from the origin, and then the displacement increases rapidly.
Yes.
Velocity, the rate of change of displacement, will be constant. Slope of tangents on points of the parabola will be the velocity.
Correct.
Velocity is assumed to be linear here.
Correct. So as we did, we'll again find the velocity at a point on the curve by drawing the tangent, right? So once we
Okay.
get that calculation, then that point and the origin can be joined and extended to show the velocity in that interval. In this case, the interval is from 0 to 4, correct? So
Mhm.
this is the part which we did in the previous example. So that is how you'll do when you get it as a part of your position time function, because any part could be curved surface, correct? So
Right.
wherever there's a curved surface, as it is in 0 to 4 interval in this particular example, you could find the displacement, which in this case is 8 meters. Velocity is linear in this. At origin, it is 0. V2, which is displacement over time, change in time. So in this case, we are checking at V equals to 2. So 4 divided by 2 is 2 meters per second. So I marked a point at 2, right? So this is my scale at 2, right?
Mhm.
Connecting 0 to 2, I get my velocity time graph
For that, yeah,
for
part.
this interval, which is from 0 to 4 seconds. Perfect.
Okay. Yeah.
Others are known to me. This is a straight line, constant, so it is 0. Here it is negative. So we can again calculate the slope of this triangle, correct? Negative, of course. So this red line here indicates the negative -2
Mhm.
velocity, which is rise over run, clear. So we get this in the third interval, -2 meters per second in between 0 and in the beginning. It is a linear function where the velocity is equals to time t. Okay, so it is increasing with time with gradient of 1. So that is how you can actually sketch the velocity time graph from the position time graph.
Could I
Now,
just ask?
yes,
Sorry, can I just ask a couple of questions?
sure.
So with this graph, when you do it in the exam, do you have to, if they say sketch the velocity time graph, do you sketch it on the position time graph, or do you do a separate graph of?
Separate, separate. And
Oh,
write meters per second, right? So because in this slide, I'm just saving some space. Now in
no,
a
because I was just
paper,
wondering, because you've
yeah.
done it such that it only goes up to 4, like you're doing it in the still the time
So
frame.
yeah,
So
better you do a separate graph and then you say,
okay,
well, this is my 0 to 4 and the velocity is kind of like this and this point is, label it kind of, right? And
yeah,
write velocity in meters per second. So since the units are different, you have to have a separate graph, right? Or you could color
Okay.
code it. It becomes complicated. So
Yeah,
separate
that's true.
graph is suggested, correct? Or I will write here, I'll write like this, velocity in meters per second, right? And then color code it. Do you understand?
Yeah.
So that blue color is velocity, for example.
Right.
Then you can do the same graph, but there is no need. Do a separate graph. So better to draw it just under this so that these dotted lines can tell you that what is happening in these intervals. You get my point?
Right.
So if
Okay.
I have to really sketch a velocity, let me mess this up now. So in that case, what I will do here is I'll draw directly below this, and these dotted lines will tell me the intervals working. And then I'll say, well, this is my velocity in this portion, that is the zero velocity, and this is -2. You get my point, right?
Yeah.
And so I'll write down -2 here, 0 here, and then I'll label this, correct? So
Yeah, that
that
makes
becomes
sense.
my velocity time graph.
And
Okay?
just the other question.
Yeah.
So just to double check, only curved non-linear like motion will have acceleration. Like the ones where we did like this would have no acceleration because it's
Zero,
constant.
zero, zero
Or,
acceleration. Zero.
oh, it's zero. Okay.
You're not accelerating. Correct. And
Wait, so
non-zero acceleration for when it is slow. Correct. So acceleration in the first case is 1 unit, 1 meters per second. So in this part, acceleration when you calculate, you'll find acceleration is 1 meters per second squared. Is that clear to you? Because that is the slope of your velocity time graph.
so 2 divided by 2, yeah, 1.
Yeah, let me remove this and then we'll read the acceleration part right here. Okay.
Do you say that's constant or no?
It is non-zero. Read this part. Read this part.
Acceleration. The rate of change of velocity is 1 meter per second squared in the interval 0 to 4.
Yes,
Acceleration is 0 thereafter.
correct. So both are constant, but it is non-zero when the velocity is linear. You get my point. Non-zero. One.
Non-zero. Okay.
Non-zero. One, right? One is not zero, correct?
Right. Wait, but then when do you say like the acceleration is constant?
Both are constant accelerations. One is also a constant value.
Oh, okay. So I can say the acceleration between 0 to 4 is constant of
Correct,
1
yes,
meter
yes.
per second squared. Okay.
Yes,
And
it
then
is
the others I'll
constant.
just say it's constant but at 0.
Yes, but zero value. Correct.
Okay, cool. Yeah.
So that is the difference, correct.
Right.
It is like, when you stand still, the velocity is constant. It is zero.
Right.
Stand still.
Yeah.
It is not changing, correct? The same
Yeah.
concept.
That's true. Yeah. It's when you put it all into the graphs, I get a little bit confused. But then when you say it like explicitly like that, it's like, yeah, that makes sense.
Correct.
So, okay.
Now, example 7. Can you please read this example?
Yeah. Use the graph to answer the following questions. A, find the average velocity on the interval 0 to 4, both included? Or is that just brackets?
Yeah, 0 to 4 is the interval. Yeah.
Okay,
But
yeah.
we will say not including. But I mean,
It doesn't really matter.
yeah,
does
in
it?
between.
Yeah.
Correct.
Okay. Wait, should I just read all of them and then
Yes.
we'll go through the answer?
Yes,
Okay.
yes.
B, find the instantaneous velocity at t equals to 8 and t equals to 10.
Yes.
C, draw a velocity time graph in the interval between 8 to 12. And D, find the acceleration in the interval between 8 to 12.
Correct. So basically, we have learned all these skills in this particular video in first 6 examples. Example 7 is like combination of all of them, right?
Oh,
so
right.
I hope you are comfortable answering all the 4 questions, correct? Find the average velocity in the interval 0 to 4. So what will you do to find average velocity in this interval, 0 to 4?
So change in position. So for change in position, which is D4 minus D0.
Yes.
So what's
8?
D4? 8 minus 0,
Yeah.
which is 8. And then divide by the change in time, which is 4, because it's 0 to 4 seconds. And then 8 divided by 4 is 2 meters per second.
Perfect. How will you find instantaneous velocity at t equals to 8 and velocity at t equals to 8?
Okay, so so you go where t equals to 8. which is a straight line, and you would, if it was like curved or anything, you would draw a tangent. But even if you draw a tangent, there would be no gradient, so it's just zero.
Zero gradient, right?
Yeah.
Zero. Instantaneous velocity at t goes to 10, somewhere here.
Oh, okay. So here, yeah, is where you draw the curve. No, it's where you draw the tangent on the point t, where t is 10 on that position time graph. And then when you do the rate of change, so change in y over change in x, you would get negative. Well, you've done the values, but it has to be a negative because we're going down.
Perfect. And the last part is during the time interval 8 to 12, what is the velocity? How do you draw the velocity time graph?
Between 8 to 12.
Yes.
So, wait.
At 8, it is 0. We just calculated at 8 is 0. And at 12, we found it to be minus 2 meters per second. So connect these 2 points, right? And extend it till the end, right? Do you get my point?
So you just, where t is 8, you just put a point 0 on the x-axis.
Correct.
And then at 12, you put it at minus 2, and then you join the points. Oh, right.
Up to this point. Is that clear to you?
Wait, how come it? Oh, yeah. Wait, what? Why did you put a line and?
It ends here, right? This is the ending point. Done.
Oh, okay.
0 to 12. Correct. Can you please read this part? Acceleration.
Acceleration, the rate of change of velocity is minus 1 meters per second squared in the interval 8 to 12, and then 0 thereafter.
Correct. And even before that. So minus 1 is the slope for this particular line, which gives you minus 1. So the slope of this is minus 1, and that is your acceleration, right?
Yeah.
So that is where we are going to close today's lesson. I hope you have understood all the concepts. So how do you find it?
That was actually really clear. My teacher's been ill for this whole time. She's been isolating. So I was kind of like really iffy about the whole, like this whole topic. But now it's like really clear in my head, like when questions are asked. Like I didn't actually know the actual meanings of any of these things and how to read them off a graph. I just thought I should memorize it, but that's not the way to go about it, because otherwise you have to actually understand it. So yeah, now it makes like really clear sense. So I know how to, like, if it's a position time graph, I would know how to draw a velocity time graph, and then from there draw an acceleration time graph. So yeah, all good.
When in the next unit, actually, we'll consider more changing velocities and accelerations, so that'll be more interesting. But this is to give you a sound foundation for.
Yes, perfect. Thank you.
So thanks a lot. See you next time, and we'll move further.
All right. Thank you, sir.
Thank you.
Bye.
Bye.